Hello guys, so welcome back to our VHDL lessons. So we're gonna continue our journey with the multiplexers, and in this recording, we're gonna explore, this interesting application basically of implementing functions using multiplexer. We take this example in the lecture in which we implemented the f of x, y, z, which is a summation of four minimum terms, 1, 2, 6, and 7. And we explored or discussed or studied two designs. One of them is basically using a 4x1 mux, and the second one was 2x1 multiplexer. Okay, so let's start by the first one, the first implementation using a 4 to 1 multiplexer. Basically, we have a package. I created a package out of this design that we explored maybe in the first recording about multiplexers. Okay, and if we remember this, this multiplexer has basically four inputs, but I combined them in one input, and this input is 4 bits. Okay, and of course the output is always 1 bit, and we have 2 bits for the selection. Okay, so this is basically the example that we should, or this is basically the solution that we should implement. So we should have a mux instance, a package, I mean, and then we should connect x and y to s0 or s1 and s0 respectively. Then we should connect the first input to z, second input to z bar, third to 0, fourth to 1. Here it is. Here is the mux 4 to 1 package that I instantiate or include in this project. Here is the input and output of the function. Basically, this implementation is for the function. So our inputs are, x, y, z, and our output is f. Okay. I mean, if we want to include, so let's draw it here. So the basic implementation that we want to implement is basically a box like this. This box has 3 inputs, x, y, and z, and one output which is f. What's inside the box is basically what we see here, this thing here. This is what inside is a box. So the box has 3 inputs, x, y, and z. That's what I have defined here. And one output which is f. Okay, good. Then we define our architecture or the design basically itself. So in that design, we need some signals to accomplish something. So for example, we need a signal that I call S, which is 2 bits. And in this signal basically to represent the selection bits here. Because the selection bits of the 4x1 mux is an input that has 2 bits of length 2. It's a standard logic vector. So S, as we see here, this signal that I call the S is basically the concatenation between X and Y. Okay, and in that way, this means X is the bit X, or the bit that will represent X is 2 to the power of 1. It's bit number 1. And the bit that represent Y is bit 0, or 2 to the power of 0. This is important, basically. So S0 is connected to Y, S1 is connected to X. This is S1, this is S0. The least significant bit is S0, the most significant bit is S1. Okay. We need another signal to represent Z bar. So I defined another signal called the node Z. You can call it whatever. It's a standard logic, of course, and it's just node Z, the third input. And this mux, remember, has this input here, which is basically 4 bits. So these 4 inputs are basically one input, but this input is 4 bits. And I call it I in the original design. So I is 4 bits, as we see here. Here are the 4 bits. Z concatenated with not Z, second one here. Then 0, then 1. Okay. Then I instantiated the 4 to 1 mux and just connect, or connect basically what our signals, our inputs and outputs to this mux. So the output of the mux should be basically the same output. Look, if, so the output of the mux here is if, the output of the design is basically if. That's why the third bit here is if. The selection of the mux is basically x and y, which we have here in a separate, in a created signal that we call s. And then the input of the mux, which is a variable that is 4-bit, is I. We have constructed it here. Okay, that's basically the first design. Let's explore the second design using 2x1 mux, which is really easier. So again, I have here the 2 to 1 mux. Okay, and again we have the design that we want to implement. Again, it has 3 inputs and 1 output, f, x, y, z. What's inside this box is basically that thing. Okay. So this mux has 2 inputs and a selection. First input is basically y, x, or z. So I created 2 signals here. One is called I0, which is basically this one. And the second one is called I1. So I0 is basically x or y, x or z, I'm sorry. And I1 is basically y. Here I am instantiating the mux and just connect my inputs and selection and output to it. So the mux will take first I0, then it will take I1, then the selection is X. And if you guys remember, this mux 2x1 have an enabled signal, inverted logic enabled signal. So I make it enabled, all the time. So I send a 0 because it's in negative logic. The enable is negative logic. It must be 0, so the design would be enabled. So I send the 0 all the time. And finally, if, which is the output. So the output of the mux is basically the output of the design. Okay. These are basically the 2 inputs. Let's try that one here. So simulate, start simulation, work, and mux function 167 version 2 test bench. Let's also have the design on a side here. The truth table is important. This design is really easy to check because it's basically just 3 inputs. So let's we need only these are 8 combinations, just 8 nanosecond. Let's change this to nano and make this 8 or maybe 10. Give it 2 extra ones. So, and here it is. Look, we start by 3 zeros. We have 0, 0, 0, 1. We have 1. This one here. Then 0, 1, 0. We have 1. Then 1, 1, 0. We have 0. That's right. Then 0, 0, 1. So x should be here. Yeah. Y should be here. Yes. Then 1, 0, 0. 1, x is 1. Then y and z is zeros. Give us 0. Then 1, 0, 1 will give us 0. That's good. Then what else? Yeah, 1, 1, 0. X1, Y1, Z0 will give us 1. and finally 1, 1, 1 will give us 1. Just to follow the truth table. Okay, really easy one. Okay, guys, that's it for the the implementing functions using multiplexers. The first example in which we have two designs. In the next video, we're gonna explore the second, example in which we have a more complicated function. Thank you very much for watching this video and see you in the next video. Bye bye.